I have added a more powerful amplifier, like this. And this was problematic because I had self-oscillations at 50 megahertz and also at much higher frequencies when I tried to kill by putting capacitors here and there. Now, there are some capacitors at various places that I have not placed in this diagram because they are not really doing what they should. They change the frequency response in an undesired way. But I have got the unit working, sort of. Here is what I see with the PN2060. And the previous result I had is this. And the differences are not so big. Most clear here, the bootstrap thing, meaning that the voltage on the drain of the first FET, the source follower, is not exactly that on the gate. So I see some of the noise from the gate-to-drain capacitance. And that's probably because I put some rather big capacitors to stop oscillations, so the phase shift or possibly the amplitude has changed on the signal on the drain. But power is much higher than before, and noise at 1 Hertz looks like 130, well, even minus 140 dBc per Hertz. Now, the effect of having the same oscillator feeding into the box and as the reference oscillator, that's something I'm not really sure will give a correct estimate on the performance of the unit as an amplifier. But at wide separations here, it's about the same as before. So now at the higher power level, I can try to measure the white noise floor when there is no signal in the box and compare it to the signal level when it is oscillating, or rather, when it is fed with the appropriate signal level from the Wenzel oscillator. The signal level into a 50 ohm load is 9.45 volts peak to peak. That's 220 milliwatts or 23.4 dBm. The output impedance is reasonably close to 50 ohms. It says 61 ohm resistive and minus 7 ohms reactive. This is a standing wave ratio of 1.27. I have verified that the noise figure is still 2.8 decibels. And now when I connect, here was the dummy load, shows 0, and when I connect my device under test, I see 6 decibels. So the noise is increasing properly. The noise figure is 2.8 decibels, means that the noise factor is 1.91. That means that the system temperature of the Perseus with its low noise amplifiers is 0.91 times the room temperature, which we set to 290 Kelvin. So the Perseus is 264 Kelvin. With the room temperature dummy connected, I see 290 from the dummy plus 264 from the Perseus means 554 Kelvin. Then when I connect the device under test instead, the noise goes up by 6.25 decibels, means a factor of 4 times, 4.22 times. So the system temperature with the device under test is 4.22 times 554, means 2338 Kelvin. And to get the temperature of the device under test, I have to subtract a little contribution from the perceives, and then I find it is 7.15 times 290, and that is 8.5 decibel. So I know room temperature means minus 174 dBm per hertz. This device I have now is 8.5 dB more noisy, so it is at minus 165.5 dBm per hertz. Now the carrier is 23.4 dBm, so the noise, phase noise plus amplitude noise, is the sum of those, where the difference between those becomes minus 188.9 dBc per hertz. And equal amounts of phase noise and amplitude noise, because this is white noise which is unrelated to the carrier, so it is 3 decibels below that. Means I have found phase noise is about minus 192 dBc per hertz. As it happens, minus 192 is in a fair agreement with the PN 2060, which is here around minus 190, but with the circles indicating that it hasn't converged yet. And here is some kind of interference, stretching from 10 kilohertz up to 100 kilohertz from the carrier. I can use the perceives to look at the noise floor near the carrier frequency. And what you can see here is there is some leakage into the box. This is the Wenzel oscillator. These two are other oscillators at 10 megahertz somewhere. One is for the measuring instruments and another, I don't know. But the interesting thing here is that the noise floor here at about 44.5 decibel on this relative scale, that is the noise floor I just found to be about minus 192 dBc per hertz. But at the carrier frequency, the level is about 61. So 44.5 up to 61. That is 16.5 dB. And that is the thermal noise of the crystals, presumably. Or maybe noise generated by the FET when it looks into the much higher impedance that the crystals have on the resonance. And you can see here there is a minimum. It seems like that at least. Anyway, if you compare this side to the other side, you can see here is more noisy. This is because I have not properly adjusted the compensation for the parallel resonance. So it is overcompensated, I think, so we have it on the side. So I could correct that, and I don't think it will matter at all when I make an oscillator out of this. Now I can switch off the Wenzel oscillator. The power supply is here. So, and it will take some time before anything happens, because there are very big capacitors there to keep the DC supply stable. But eventually the oscillation will stop. Well, the Wenzel has disappeared. You can see it drifts off here. Then it takes some time, because I have 190 averages on the baseband spectrum. But there is still a signal a trifle lower than the Wenzel. This is my channel 2 oscillator, which is now free running. Normally it would be locked to the Wenzel oscillator. And these two signals, they are these two, I guess. Here, I don't know. I have started the Wenzel oscillator again, and here it comes drifting, and you can see it here also in the averages. And it will take some time before it has stabilized. I have changed the tuning here, making this inductance a little smaller. This has caused a loss of 1 decibel on the output power here, but it has affected the time delay from base to drain. This clearly shows the problem. Here is the running experiment after that mistuning, and here is what I had before I did that. And there is a significant change here. I have not waited long enough to have a flat spectrum, but it's clearly reduced now, this thing that comes from the noise in the base to drain capacitance. This structure here that varies from time to time is this thing here, which varies when I move wires around the box or cables or things. So I will improve screening to see whether I can get rid of it. I have used copper foil to join both sides of the PCB laminate to improve screening. And clearly the spurs from other 10 MHz oscillators around here have decreased. The Wenzel oscillator, or possibly my channel 2 oscillator, are much weaker, and here is only one strong spur. There were two before. To make sure that the minus 92 dBc per Hertz I have determined for my oscillator, or at this moment selective amplifier, I need to verify that the noise floor does not change when the strong carrier is present. To do that, I use this filter. I will have the device under test and then take out the signal to the normal signal analyzer. And through these crystals, I will pick up a signal to send to a sensitive receiver. And to do that, I need a notch filter here also. And I will show with a network analyzer what happens with this arrangement. Here is the 10.7 MHz filter. It's terminated in a 50 ohm dummy load to simulate the normal sideband noise measurement system. And then is the output at 10.7 and a notch at 10.0, and then into the network analyzer again. And here is what I see with a wide span. There is a notch at 10 MHz and transmission at 10.7. The attenuation at 10 MHz is about 80 decibels. When I remove the dummy load that simulates my sideband noise test system, then the impedance goes up to 50 ohms, because the signal is no longer split in two paths. On 10 MHz, the impedance is 50 ohms, means that the strong signal from the unit under test looks into its nominal impedance, as it should. And of course, when I disconnect the dummy load, so the port where the phase noise analyzer normally is connected becomes open, then the impedance I see looking into the filter is very high. So the 10.7 MHz filter does not load. Of course, otherwise I wouldn't have seen 50 ohms with the dummy in place. I have reduced the inductance of this coil a little further and lost another half a decibel on the signal level. This has improved performance around 10 Hz. Here is the previous result, and here is 0.5 dB less power. I have compensated with the attenuators in front of the PN2060 to have the full signal level here into the PN2060. I will insert 20 decibels of attenuation from the Wenzel oscillator and reduce the attenuation in front of the PN2060 by 20 decibel. That is to see what happens with these interferences. With the carrier attenuated by 20 decibels, that is the input to this selective amplifier, of course the flat noise floor will lift by 20 decibels. So minus 192 up to minus 172. That is a very good agreement. And I have reduced the carrier power by 1.5 decibel. So it seems the noise has gone down by 1.5 decibels also. And what has happened here is a difficult thing. If I look at the previous, here is the full signal level, and here is what I have with 20 decibels attenuation. I see the characteristic shape here that I associate with the phase noise introduced by phase modulation from the base collector capacitors of the source followers. And why it behaves like this, I don't know. What I was waiting for is this structure. If it were introduced inside the device under test or in the cable from that to the hybrid, then I would expect this to have increased, because I have increased the sensitivity of the PN2060 by 20 decibels. So the fact that they are essentially unchanged seems to indicate that these things are coupled into the system on the other side of the hybrid. There are some amplifiers and attenuators and connectors and stuff. So somewhere there is a leakage of these spurs. Then, very close to the carrier, here, I see no difference. Well, I don't know what to say about that really. I have connected the 10.7 MHz filter and the 10 MHz notch. And then this signal goes further to the Perseus, and this one goes to my phase noise analyzer. Here is the noise floor of my selective amplifier when there is no signal sent into it. And I have the PN2060 running at the same time here. And you can see this is the noise floor. I connect the Wenzel oscillator at normal signal level now. A big transient, of course, but then not much happens to the noise floor. But you can see here 9 dBm, that's the normal signal level. And if I start measuring, we don't see it here, but you can see down here everything is normal. And I can evaluate the noise floor. I wait a little longer to get better statistics. And it says 0.09, and before it said 0.005. So now I waited a little longer and I check it again. 0.086. So the noise floor may have increased by 1/10 of a decibel. And if I look here, the level of the carrier,
It goes far outside the graph, and I don't care to try to evaluate because there is no calibration that I can use. So I go back here and try to sit on the same spot, because now I can replace the device under test by a 50 ohm dummy load. And now the signal level is significantly lower, which means that what I see is really the noise floor from my selective amplifier. This is about 3 decibels.
Trying to avoid self-oscillations, I have added a resonant circuit here. So this coil with 180 pf makes a fairly broad resonance at 10 MHz. Trying to stop oscillations at higher frequencies due to the feedback this way. Now, this was not very successful. I had to put a resistor here, 27 ohms, to not have oscillations. I reduced this inductor, trying to balance the 100 pf capacitance here. And the result is that the voltage here is not the same as on the gate. It has the correct phase, but the amplitude is significantly lower than on the gate. Trying to fix that by tuning on this or that creates self-oscillations. Here is the result. I see the noise from the gate-to-drain capacitance here. I can compare with the best from before, which is this, when I had 1.5 dB degraded power by mistuning something. So it is very similar, with the exception here, where the degradation is something like 5 or 6 decibels, or here, from here to here, maybe 8 decibels. But I have a problem out here that I don't know what it is, but that has some interesting consequences when I change the tuning. I have a power splitter and I'm running linear in parallel at the same time. So it is directly on the output of the device under test. And I have a 10 dB attenuator and 10 dB attenuation here also. And the level is close to saturation for the perceivs. And there is no preamplifier. But I have normal signal levels for the PN2060 and also for the perceivs. When I change the tuning of those inductors, the series and the parallel resonators, I can easily run into self-oscillations. And you can see the structure here and here. This is 10 kilohertz, this is almost 1 megahertz. 10 kilohertz, 1 megahertz. And the noise level is high. Now I am operating directly from the power supply, because having big capacitors is not so good when you do experiments. A short circuit will damage things. Now I connect capacitors, and you see a big change. The supply voltage has not changed. I can restart. And you see, all the structures are gone. It is still self-oscillating, but now it's not modulated by the power supply, so it gives a very different structure. But the noise here is the same. So I have to do other things to get rid of the self-oscillation problems. Trying to be more systematic, I disconnect here and here to isolate the amplifiers from feedback loops and so. So I want to study this amplifier while this one is hanging on, having its capacitive loading here as it will have later on. Here is the point where I want to know the impedance. And this capacitor goes to the network analyzer. And now when it's hanging free in the air, I calibrate the network analyzer for open. And then I solder the capacitor to ground here to calibrate for short. And to calibrate for load, I just place a 50 ohm dummy load directly on the network analyzer, because there is a 50 ohm coax all the way to the box where I do the testing. And now I can measure the impedance here on the common gates of the output amplifier and the feedback amplifier. I now look at transmission from this point to this point. And I expect a voltage gain of unity. The network analyzer does not show the voltage gain, it shows the power gain. And it's more than 0 dB because the signal coming from the network analyzer is not loaded by 50 ohms as is supposed. So I see a gain of almost 3 decibels, 2.96. But the peak is, as expected, on 10 megahertz where I tuned the input. And these other structures, I don't know, but I have problems at about 50 megahertz when it wants to oscillate. The phase is very close to 0. It says -7 degrees. I have reconnected here and disconnected here instead, and now I feed the signal from the network analyzer into the inductor. Here is the impedance. It is resistive and 960 ohms on 10 megahertz. And here is the frequency response. Looks a little bit odd, but this is what I get. And the old trace is here. That is without the series resonator. I have reconnected here and instead connected the signal from the network analyzer directly to the basis of these 3 parallel J310. And I have the other network here with the crystal still hanging on. The amplitude response is unchanged. That is expected because I force a very low impedance on the high impedance point of the gates. The phase response has changed significantly, as you can see. And here is the impedance at that point. It is capacitive and very low resistive component. When I reduce the frequency span, I can see the effect of the crystal. The impedance is very high at the resonance a little bit above 10 megahertz, and there is a low impedance point also. I send this signal into the gates of the source following FETs. It is a low impedance signal, and I measure it with the 2 channels on my oscilloscope. And of course they show something very similar. And then I invert and take the sum. Means I have the difference between the curves here. And I want that to stay flat when I go through the amplifier. On the sources, the level is slightly lower. As you can see, there is some signal here on the difference. On the sources of the next amplifier, where I should couple into the drain of the first FET, there is a significant amplitude difference, and there is also a small phase shift. You can see that this difference is largest here.
When I disconnect the network analyzer, which was presenting a 50 ohm load on the sources of the amplifier, I get oscillations, as you can see here. These oscillations disappear already with a 10 pF capacitor, as you can see here. And when there are oscillations, the channel 2 curve is distorted also in amplitude, which is clearly visible here. I can change the tuning of the parallel resonator on the gates of the output amplifiers. And I reduce the inductance, and here the signal on the gate of the source follower and of the drain of the source follower is now very similar. Now the voltage on the source and on the drain are almost identical. Here the AC voltage on the drains of the 3 source follower FETs very accurately equals the AC voltage on the gates. And then I don't see this curve here, it's a straight line. This has been running for about 24 hours, so statistics is good. But here, below 1 Hertz, I only see noise. The previous result I had here is significantly better, as you can see. But now the power is limited. I cannot go above 25 microwatts in each crystal, because then there is a saturation problem. This result with a 6 decibel weaker carrier is very interesting, because maybe when I increase by 6 decibels, I might get 6 decibels below. Here is the current circuit diagram. I have mistuned the series resonator and the parallel resonator, and also change components, 2.2 nanofarads and 0.8 microhenry, 0.82 nominally. And I have added some resistors and capacitors to stop shelf oscillations. And I am loading the amplifiers with 50 ohms, both here and here. And I have added also a 68 ohm load here to prevent oscillations and so on. And the result of all these things is that the AC voltage here is exactly the same as the AC voltage here. And then, to make things work, I had to add a trimmer inductor here, because it's essential that the sources of these 3 FETs see a resistive load. Even 5 pF here creates feedback and makes this a negative resistor. And it is very sensitive, and it should be regulated by this tuned to a resistive, and the series link transferring that resistive load to this point. But that didn't give me the right voltage on the drains. So I have compensated that with this tunable inductance as a temporary solution to test how this works. And you have seen a pretty good result, but when I turn up power, these amplifiers go into saturation. That changes the impedance in this point, makes it more capacitive. When it becomes capacitive, there is a negative resistant here as the gate. That brings up the gain, increases the crystal current, and runs these amplifiers then into heavy saturation. And then the result is a noisy signal. Here is how it works. This is the crystal current. 18 millivolts peak to peak means 36 milliamps. Divide by 20 and compute the power in a 65 ohm load for an individual crystal gives me 26 microwatts. And then the upper trace is the voltage on the drains of the amplifier providing the signal for the drains of the source followers. And I increase the signal level 1 dB, 2 dB, and there you can see something. So this is that the impedance on the source follower changes and it goes into a non-linear mode. And that is because something is overloaded. And I will look into this and see what I can do about it. I have removed the 50 ohm load that is on the output port where I normally would put the feedback to make an oscillator. So now that is open and it's more clear what happens. I increase the signal level 1 dB, 1 more dB. You can see some saturation in the output. And suddenly, now I decrease. And 1 more dB, and 1 more dB. And it's still saturated. That's because the input impedance to that stage is now capacitive, and that causes a negative impedance on the gate. And you can see the crystal current, it is doubled. I attenuate 1 more dB, and then it goes into linear operation. And you can see the crystal current is weaker than this level where I was running. So I understand the problem, I think, and I can do something about it, I think. Something bad has happened to my selective amplifier. Now it is very noisy. Compared to before, if you see here, it differs by about 40 decibels in this region. Maybe this is because I made a mistake, forgetting that I was feeding from the filtered power supply, so I happened to discharge 1.5 farad inside the box. And that made a giant transient that might have destroyed some transistor. Or perhaps I have just introduced a noisy component somewhere. To find out, I repeat the first experiments in nerds111. I did not add this series link to kill oscillations. I added instead 330 ohms from this point in series with 47 pf to ground. That also kills the oscillations. I see the same signal level as before, and I see the same power at this point, and the impedance is 50 ohms. I have not gone back to the exact schematics from then. I have not changed anything on this side, and the frequency is the same within 1/10 of a hertz. So I can do the measurement and see what has happened to the noise floor. I have disconnected the 3 FETs down here and instead placed a new one here. And this ferrite bead, I don't think it made any difference, so I left it in place. And this resistor and capacitor is what kills the oscillations. And 1 nanofarad in series with 36 ohms makes the impedance 50 ohms at the output. What I see now is not too different from what I saw in nerds111, which is this. You see here, it's a little bit more noise from the drain to gate capacitance, but here at 1 hertz, very much the same. And out here, I have not been measuring long enough. it is 2,700 averages now, and here it was 15,000. So it is clear the problem is not the noisy component among the capacitors and other stuff on the crystal side. It is in the amplifier side, probably with one of the FETs, or more of them. I have removed the extra FET and connected the 3 ones in parallel to the transformer. There is also a large inductor to ground. I think that is insignificant. And now I can see whether these 3 transistors work as they should. Here is what I see, and the noise level is high compared to here what I had from a single transistor in the nerds111. I restart because it looks not so bad initially. So it means something must change with time. Now it looks normal. Here is the old from nerds109, and here is what I see now. I don't know why it had such high noise when I was not present here. I will leave it running for a while to see what happens. After 7 hours, I see a very noisy phase noise spectrum. So something has happened. But this time I made a time-lapse video so I can play it and see what happens. Here is what it should look like, and here is what I have. Here is the time-lapse video. I started, and it's building statistics, improving here and increasing downwards. Oops, here is the problem, an instability of some kind. Before the event I see 7.970 and I step some frames forward and it doesn't change. And here something happens, 7.964, and we see the transient here, 961, 9695. So there is some instability, and if I continue, it varies significantly, and I stopped it here. So this is not the regular steady noise I was seeing before. It is an instability. When I connected the second stage, this one, the steady, strong noise came back. So there was a problem here. When I measured the voltage on the sources, I found that one of them was much higher. Means that the channel resistance was much smaller. So I replaced all 3 because the problem was the one in the center and I could not remove it without destroying the other ones. They are glued to the box for cooling. Now things look normal. Q is 1.037 million. I've changed the span to 1 Hertz per division. And then I read from the marker information that the attenuation at 1 Hertz offset is about 0.15 decibels. Now the unit is okay again. This has been running for 24 hours. And if I try to estimate the noise at 1 Hertz, I find it something like minus 136. And at 10 Hertz, the marker seems to be in a good position, so I can read minus 156. And 100 Hertz here, I would say minus 175. And above that, there are circles everywhere. This has not converged. And below 1 Hertz, the same, it has not converged. Here is the schematic diagram for the recording you just saw. I have changed some things. This amplifier is now in series with that one. Before they were both connected to this point, which made tuning more difficult here, and the impedance, which is very critical, was affected by the load on this amplifier. Now this is more of an isolation amplifier, and it does provide the signal to the drain here, and it does provide input to the second amplifier. Now there is a 100 pF capacitor here. That is to prevent self-oscillations. I have now made this inductor adjustable, and I tune it by replacing this inductor by a 50 ohm resistor and apply a signal here at 10 megahertz, and then I tune this one for maximum signal. It gives a sharp resonance, of course, and that is without this capacitor connected. So it's only the transistor and this capacitor and the inductor. So they balance each other when tuned. I had before tuning on the source, no longer, because I needed that coil for this purpose. Later on I will add the tuning here, because I can tune this one and that one to get a perfect agreement between the source and the gate voltage. But when I do that, I don't get the correct impedance loading on the source. So I had to tweak this one or that one a little bit to restore a high impedance at this point. It must be no reactive component on the source, because it gives negative or positive feedback here. And I want to have the load on the crystal with a very high impedance, non-reactive here. And absolutely not the negative impedance, which I can get by putting a capacitor here. Whether a small capacitor would improve by the improved Q, I don't know. It takes a very long time to test things now, so I will not do any more changes to this. The next step will be to try to make an oscillator out of this. And that means finding a way of limiting the amplitude without introducing noise. And I don't have a solution to that problem at this moment. Everything I have tried so far with other oscillator experiments has been a little bit noisy, and at the levels of noise I see now, they would be disastrous. So I have to figure out something better. There is not so much anymore to prevent self-oscillations, because now I'm using bifilar windings on a T50 of material 2, and I only have a 150 pF capacitor from drains to ground, and this 180 from from source to ground. And both of them have to be placed very close to the transistor. And then this amplifier, I only have a big capacitor on the drains. And it doesn't oscillate. This is a trifilar winding to bring up the voltage on the drain to give a 50 ohm output when there is 33 ohms in series. Here is the setup I'm using. I have not included all amplifiers that are somewhere in the lines. The Wenzel oscillator, which has minus 120 dBc per hertz at 1 hertz offset. I amplify it a little and split it into 3 channels. One goes into the unit under test, which is a filter and an amplifier. One goes into the PN2060, and the third goes to my PLL system that locks the channel 2 oscillator to the same frequency. This is not at all necessary in this setup because the PN2060 can work with different frequencies on the references. But when I use the setup with my Linrad system, then I need this because I use another way of detecting phase and amplitude modulation that requires both channels to be very close in frequency, within 1/10 of a hertz or even 1/100th of a hertz. The PLL has an extremely long time constant in minutes, so fast variations in the Wenzel frequency do not affect the frequency of this local oscillator. And these 2 signals go into the PN2060. The interesting thing of this, if we think about a signal very close to the carrier, these 3, those 2 plus 1 reference, the Wenzel itself, contains the instantaneous frequency of the Wenzel oscillator. So what this unit does, it mixes them, means take the difference frequency, and for device under test 1 and reference 1, both contain the same frequency drift from the Wenzel, so the difference frequency is independent. But the other channel, when this one is mixed with the output here, I get the noise of the Wenzel. But when taking the correlation between A and B here, since it is not present in this in the A channel, it is not present in the correlation channel either, if we average over a long enough time. And this is, I think, not used normally. I could use it to evaluate noise below 1 hertz, but at 1 hertz there is a problem. I want to figure out whether it is a problem or not. The phase noise of the Wenzel at 1 hertz offset is minus 120 dBc per hertz. The filter attenuation at 1 hertz offset is 0.15 decibels. That is a factor of 0.9825 in amplitude. Mixing the Wenzel with its filtered version does not fully remove the sidebands at 1 hertz offset. 1 minus 0.9825 will remain. That is 0.017 of amplitude that will remain. And that is a factor of 0.0003 in power, so it is very small. The remaining noise from the Wenzel at 1 hertz offset then would be minus 120 minus 35. That is minus 155 dBc per hertz. And that is far below the 136 that I have seen, so it isn't a problem. To verify the method, I have replaced the device under test by a BNC female-to-female adapter. Now I should see the noise floor of my system. And it is the noise floor of my channel 2 oscillator that will average out and disappear. But it's also the noise of the PN2060 itself and some amplifiers and maybe other stuff that are in the total system. So I will wait for a while and see how far down this will go. This is 1 hour. I can compare it with my result for my selective amplifier, like this. And it's clear here that this is actually the amplifier. But outside this range, after 1 hour, the noise level is higher than what I had with the amplifier. So I will wait for a while to see what is the noise floor of my test system. Here is 12 hours with nothing as the device under test. To compare with this, which is my selective amplifier. The difference is small except here, where I have noise from my amplifier, while the system performance is something like 10 decibels better than that. But otherwise, it is very much the same. Here, it is hard to say, but anyway, the performance is not quite adequate, except between 1 Hertz and 10 Hertz approximately. Or let's say 2 Hertz up to 30 Hertz, where I clearly see. And of course it is also visible as a less noisy trace in this region, as compared to this, which is noise only. An interesting feature is the gray line we see here. It is absent here. I don't know what that means. Here is 12 hours with nothing as the device under test. To compare with this, which is my selective amplifier. The difference is small except here, where I have noise from my amplifier, while the system performance is something like 10 decibels better than that. But otherwise, it is very much the same. Here, it is hard to say, but anyway, the performance is not quite adequate, except between 1 Hertz and 10 Hertz approximately. Or let's say 2 Hertz up to 30 Hertz, where I clearly see. And of course it is also visible as a less noisy trace in this region, as compared to this, which is noise only. An interesting feature is the gray line we see here. It is absent here. I don't know what that means. The noise level is again very high. This is what it looked like in the morning. I stopped it and restarted, and here is what it looks like now, even higher. And I can see the amplitude now is 9.1 dBm in channel 1, the DUT1, but in the morning it was 9.3, and I have not changed anything. So something is changing to the worse. Now, in the late evening, it looks very different. I don't understand what's going on. This is one of the previous, and now it looks like this. I have measured the source voltages of all the transistors, and there is no difference from what it should be. Maybe it's the crystals that have failed. I have disconnected the amplifier and put another JFET like this that I did in nerds111, and now I'm measuring what I will have. Here is what I saw in nerds109, and here is what I see now. And I It is too early to say something. I wait a little. Well, I don't have to wait. There is a big problem. And I can see also here so something is wrong among the crystals or with capacitors or the transformer for cancelling or for suppression, the stop band. But I think it's the crystals, and I have a little theory why. Because I have set the crystal current for an average power of 100 microwatts, but I don't know for sure that the crystals have the same inductance at the frequency where they operate. And I did, when I select them, measure them at room temperature. But now I know that the temperature coefficient may differ significantly. So I have another set of crystals that were selected for the same series resonance at about 78 degrees. And they should have similar inductances to a much higher accuracy than the ones I have been playing with now. And you see here the noise. It is very much higher. Now it seems like the unit has repaired itself. I have not done anything that could explain why it's now like this. Here is the old from nerds111. Here. And now it looks like the signal, the noise is below that. I'm stunned. It looks like whatever went wrong has repaired itself now. If I compare with that old nerds109, it's here. And this is significantly better, and it has not converged yet. So I will reconnect the amplifier with all the many transistors to see if it is perfectly okay. Measurements are slow. It takes 24 hours to get a good statistics or a reasonable statistics. So I tried to see, can I find a better level for the signal. Standard I have been using is 9.5 dBm. Maximum is 10. So if I go down from 9.5 to 6.5, this is what I see. It is a little bit more noisy. The other direction, above specification, that's 12.5 dBm. And I compare it with 9.5. Difference is very small. I also tried 6 decibels above. That's here, 15.5. And it is better. 15.5 I compare with 9.5. So after maybe only 10 hours, the statistics would be good enough here. I wanted to try somewhat longer time, so I made measurements over 3 hours. So what you have on screen now is 15.5 dBm. You can see the text here, and only 30 averages. And in 3 hours, this is what I see. And it looks fairly good, but not out here. The noise level looks a bit high. But 136, if I try to see here, 158 at 10 Hertz. And then I tried 9.5 dBm, the standard level, and it failed because the noise level is now high. I think this is from the crystals. On the other hand, at wide separations, the noise seems to be very low. It hasn't converged yet. It will go below 190. So maybe the out-of-spec signal level is an improvement around 100 Hertz or 1 kilohertz, but it is a loss at wider separations. Now, I don't really know, and I have not been able to get rid of this noise. So I stop this video here, and I will start with a better crystal oven and crystals that are selected to be the same at the operating temperature. I think this video has showed that there are possibilities to get very good oscillators by use of several crystals.